We've been going out to Jupiter, and then we came back to the Earth with John, and now we're bouncing back to the outer solar system. And but you know, you get used to that in the space age. So what we're going to do now is we're going to move from Mars and the Jupiter system to consider what I regard as two extraordinarily interesting objects from the point of view of the origin of life and the search for life in our own solar system. And what the success of this lecture, unlike the other lectures, will depend on how much you prioritize Titan and Enceladus above other targets for searching for life. So tonight after the concert, I'm going to start polling individuals, and of course you can. There's no grade in this class, so you don't have to agree with me, but I'll be curious as to how you feel about all this. So we'll see. So we'll move out to the Saturn system, 9.5 times farther from the Sun than the Earth is. And the first place we're going to go to is this rather surrealistic location, which in fact is Saturn's moon Enceladus. It is a body that is about 1,000 times smaller in volume than Europa. Interestingly, while we think of these smaller Saturnian satellites as being mostly icy, they actually have quite a variation in the amount of rock versus ice. And Enceladus is one of the rockier ones. It has a fraction of water ice that's almost 70% of its total mass. So it's mostly rock, but with a good fraction of ice. And what you see here are not 3 spotlights getting ready to light the stage for a performance, but these are some of the jets coming out of the surface of Enceladus. This is the surface of Enceladus itself. Of course, we're looking at it in shadow, and we're seeing the sun illuminating these jets of icy material. And what's interesting is you can see through these jets the shadow of Enceladus itself, which is quite nice. When you stand on the top of a very pointy mountain right at sunset, you can see the shadow of that mountain actually in the air, in the dust. And that's what we're seeing here.
So why did you choose that font?
I wanted to give you a sense of trepidation because we actually don't really know what's going on in Enceladus. And there's some pretty evil-looking places, too, which I'm going to show you in a minute. So this is a friendlier view of Enceladus on the left. It shows the south polar region, which has a series of fractures and also is very much melted. There are some craters on the periphery, but clearly this is a surface which, first of all, is almost entirely water ice. Spectroscopically, it's almost entirely water ice. But as you can see, there are very few craters. It's been very heavily modified by melting, by fracturing. And coming out of these plumes of material, coming out of the jets of material, are a number of species other than water ice. Now, Cassini discovered these jets coming out of Enceladus in somewhat the same way that it discovered the liquid water ocean under Europa, under Jupiter's moon Europa. It was through the perturbation in the magnetic field caused in this case by the flood of neutral particles going out of Enceladus into the Saturn magnetosphere. Thank you very much. That's great. Appreciate that. And it was only after that that the plumes were actually observed. Coming out of these plumes are CO2, of course water first, but carbon dioxide, methane, nitrogen, various hydrocarbons, ethane, acetylene, C2H4 ethylene, some evidence for H2S, ammonia, formaldehyde, methanol, possibly HCN, CH3, other hydrocarbons as well. These are compared, of course, to cometary values in the same chart that I showed a while ago. There are 2 striking things about this. One is the richness in the compounds that are coming out, and the other is the very primitive nature of the composition, because In coarse form, this isn't all that different from what you see in comets, but there are some differences, in particular the amount of N2. Now, in addition to these compounds coming out along with the water ice, sodium was measured as well, sodium and potassium. So sodium evidently is being emitted with the ice particles, was in the water, and that, along with the fact that the cracks themselves, the fractures where the jets are emanating from, are quite warm. In fact, measured at the surface to be 170 or 180 Kelvin, whereas the overall surface temperature of Enceladus is 60 Kelvin. This is pretty good evidence that if you go down into the fractures, there is liquid water.
Jonathan,
yes?
How close is it to Saturn in units of Saturn radii? More relevant is in units of its own radius?
There's very little, okay, I don't know the answer to that. It's the second moon outward. Okay. Mimas is the closest. Enceladus is the second. There's very little tidal heating here. There might have been in the past, but this is not an object which is in an eccentric orbit that's being maintained and for which there's any significant tidal dissipation. There may be some, but these jets cannot be explained by tidal heating. It's just too small. So one of the interesting questions is, what is the energy source? And the best guess is that, first of all, there's a large fraction of rock. If you start Enceladus off hot or give it a pulse of tidal heating early in its history, the subsequent thermal evolution, which actually has a hysteresis, it depends on whether you have a cold or a hot start, could maintain activity even to the present day. But there may be, in fact, because the orbit is not quite zero eccentricity, there may be small amounts of tidal heating in the upper layers. It's just not plausible that it would be the entire source of heating. So it's still a mystery, and it's an interesting one. So the fractures, one of these you see here, are really quite dramatic. This is the highest resolution image that Cassini obtained, and it provides a resolution on the order of 10 meters. And this is one of the active fracture zones. Now, jets of material are not coming out in this particular region. They come out in a spotty fashion, and they appear to move around from flyby to flyby. And indeed, apropos of your question, this activity may in fact be not continuous but periodic. One of the important things that Cassini can do is monitor this over a period of hopefully as many as 13 years by the time the mission's over. But nonetheless, currently in some areas of these fractures, there is ice coming out, and these are quite hot. So basically, from my point of view, this is at some level an easier target than Europa. There's no radiation that is of any concern in the Saturn system. The Saturn magnetic field is much, much smaller, much weaker than that of Jupiter's. Although Saturn has a magnetosphere, the particle loading and the energies in the magnetosphere of Saturn are really quite small compared to anything that would bother a spacecraft. So one can loiter in the environment of Enceladus for a long time without any problems. These cracks clearly are open to some kind of high temperature liquid water in the interior. We don't know quite how far down, but probably relatively close to the surface.
So what's the scale on that?
So the highest resolution features that you see here, the smallest features that you see, are on the order of 10 meters. Okay, so this is small scale. This is the highest resolution Cassini obtained. So you could navigate to these places because Enceladus is such a small body. Gravity is not a big issue. You could conceivably navigate a lander to these areas and drop into the cracks. But nature is providing you with material that's coming out anyway, so you might even think about landing on the edge of these cracks and trying to sample the plumes with a very elaborate mass spectrometer or other instruments. So in a sense, the next phase of Europa exploration, which was to determine where the ocean is accessible to the surface and whether one can actually access material from the interior, has already been done for Enceladus by Cassini. So we've passed that stage for Enceladus. So you can now go on to step 3, if you will, and actually put something in these regions where material from the interior is coming out. Is there life in the liquid water? Well, there are a number of issues that would make one somewhat concerned, including the possibility that these are temporary emissions. It's clearly not global. It's confined to the South Polar region. So this is not a global ocean the way it is on Europa. But on the other hand, if you found something in the interior that demonstrably was a product of biology, it could tell you some interesting things, the most banal of which would be that Enceladus got contaminated through impact exchange some time ago, and these contaminants were able to retain their viability and survive. Nonetheless, this is an important target, and one that's much easier than Europa. Titan is an entirely different target. Titan is the second largest moon in the solar system, bigger than the planet Mercury. It has a density twice that of water ice, so it's a mixture of about 60% rock and 40% ice. It is the only moon in the solar system with a substantial atmosphere, dense atmosphere. The surface pressure is 1.5 atmospheres, and the surface temperature varies from pole to equator between 89 and 94 degrees Kelvin. The atmosphere of Titan is not all that different in structure from that of the Earth. This is a plot of pressure in millibars versus temperature in degrees Kelvin. Here's the temperature profile. There's a troposphere with a greenhouse effect that raises the temperature from an effective temperature of 84 Kelvin to a surface temperature of 94 Kelvin at the equator. The temperature drops because Titan is a rock ice body that's just a little bit bigger than the planet Mercury. That's big for a moon but small for a planet. The gravity is 1/7 that of the Earth. So the scale height in the atmosphere is 2 to 3 times, depending on where you are, that for the Earth. So this is a more extended atmosphere than it is for the Earth. As I mentioned this morning, this atmosphere, like that of the Earth, is predominantly molecular nitrogen. There's a tropopause at 70 Kelvin, then a stratosphere, which is principally heated by absorption of solar radiation on aerosol particles in the blue part of the spectrum. There are molecules that participate in cooling as you get to the mesosphere, HCN in particular. There are several haze layers, a main haze layer which prevents one from seeing to the surface of Titan at optical wavelengths. And then above the mesosphere, temperatures increase again in the thermosphere, where energy is being deposited from both ultraviolet light and also by charged particles from the Saturn magnetosphere. Doing chemistry, the second most abundant material in Titan's atmosphere is methane. At 94 Kelvin, water is frozen out. So water is part of the bedrock of Titan. It's not relevant to the atmosphere, except for a small amount of water that comes in from meteorites, essentially, and also from these plumes from Enceladus, and participates in producing CO and eventually CO2, a secondary photochemical cycle. The primary photochemical cycle is with methane. In the lower part of the atmosphere, methane saturates at about 8 kilometers, forms clouds. In the upper part of the atmosphere, methane is destroyed by absorption of ultraviolet light and charged particle radiation, produces this haze, and generates a number of interesting organic compounds. So this is a thermal infrared, mid-infrared spectrum of Titan's stratosphere, where the lines are in emission because they're above a cold tropopause. So this is radiance versus wave number now. Here's 10 microns over here. And you see the emission features of acetylene, ethane, propane, hydrogen cyanide, carbon dioxide. There's methylacetylene, diacetylene, ethylene, propane. Methane is present too, but in this part of the spectrum it's hard to see. And one can see deuterated species as well. So this is generated from the Cassini infrared spectrometer data. This is, of course, interesting from an abiotic organic chemistry point of view. This is demonstrably abiotic organic chemistry in Titan's stratosphere and mesosphere, but nonetheless, it's a rich chemistry that actually continues out to very high molecular weight, because in the very upper part of the atmosphere, the Cassini mass spectrometer on the orbiter was able to sense the atmosphere at 950 kilometers. The spacecraft could safely pass through that part of the atmosphere. And what you see is a composite mass spectrum, density or abundance versus mass over charge, folded into two panels here. And these go out to the limit of the mass spectrometer, which was just 100 AMU. While the number of species are declining, they're not declining that rapidly. And there are other experiments that were able to identify heavier ions in Titan's upper atmosphere, but did not have the mass resolution to determine what they were, just that they actually exist. So if you flew a mass spectrometer with a mass to charge limit not of 100 AMU, but of 10,000 AMU, there would still be material to see. There would still be polymers to see. So the charged particle chemistry is generating polymers from methane and from nitrogen. And the net result of this is that methane is being destroyed and these products are ending up on the surface. In fact, part of the Cassini mission was to land the European Space Agency Huygens probe on the surface. This is a surface image. This is a mass spectrum taken after landing. You see methane. Actually, the methane to nitrogen ratio here is larger than it was in the atmosphere during descent. And evidently, methane was actually outgassing from the surface underneath the probe. There's also carbon dioxide, cyanogen, benzene, ethane, and hydrogen cyanide also show up. And here is argon-40, which is a product of the radioactive decay of potassium-40 and indicates that Titan's deep interior has been outgassing over time. I'll get back to that later. So the chemistry in a nutshell is this. The simplest part of it is two methane molecules, each of which absorbing a photon at less than 1400 angstroms, produce either ethane or acetylene with loss of hydrogen. The hydrogen escapes from Titan. That was observed by Voyager, observed by Cassini. And these products, which are much less volatile than methane, predominantly in the cold stratosphere, condense out to form aerosols, and those fall to the surface. At the temperature of the surface, ethane and methane are in the liquid state. Acetylene is in the solid form. Of course, not all of these condense out before more chemistry occurs and you make all these other materials, but the predominant products are ethane, acetylene, and with the participation of molecular nitrogen, hydrogen cyanide. The acetylene and HCN being less abundant than the ethane by a factor of about 5 or so. So this prodigious chemistry is irreversible. There's no source of hydrogen that we know of in the atmosphere to regenerate this material. So the net photochemical destruction rate of methane has been calculated many times now, actually since Voyager, and leads to the conclusion that all the methane in the atmosphere of Titan today will be destroyed in 35 million years. Now, that doesn't mean that Titan had 100 times this amount of methane in its atmosphere, and we're just looking at the last little bit. The atmosphere is cold, and you can't pump arbitrary amounts of methane into it, just as you cannot pump arbitrary amounts of water into the Earth's atmosphere. So the actual limit on the amount of methane that the atmosphere can store would give you a lifetime of about 100 million years or so. And so what this is suggesting is that there has been a resupply of methane to the atmosphere over time. And given the impact rates in the last half of the solar system, it's not very plausible that this has come from late infalling comets. It must be something that's coming from Titan's interior. If this chemistry has been going on continuously over the age of the solar system, one should expect to see a layer between ½ a kilometer and a kilometer thick of ethane liquid, along with whatever methane is mixed in, and about 100 meters of acetylene and hydrogen cyanide solids. We see the solid component on the surface in the form of vast areas of dunes in the equatorial regions, but we don't see the ethane. Gesundheit. Okay, so this is an attempt to show the carbon budget for Titan. This is now given in teratons instead of gigatons. I apologize for that. By comparison, the amount of methane consumed over Titan's history, if the photochemistry has gone on continuously, would be about 10,000 teratons. There are three components that we know of for the organic constituent on Titan's surface. The atmosphere, which is mostly methane, lakes and seas, which I'll show you in a minute, which have a range of possible volumes, given this is the lower limit, the inner circle, the outer circle is a sort of an upper limit, and the dune fields that cover 15% of Titan's surface. Again, based on estimates of the thickness of those layers, a lower limit and an upper limit. By the way, this amount of liquid in the lakes, which is probably a mixture of methane and ethane, is between 10 and 100 times the known fossil fuel reserves on the Earth, excluding possibly a very large amount of methane clathrate hydrate, which would make it comparable. So here's our energy independence right in front of us, if you can get it. Okay. So clearly this is a lot of material, and Titan is very organic rich, but methane has to be resupplied somehow. So the lakes and seas were probably one of Cassini's greatest discoveries. They were discovered by radar imagery. This is a composite of radar images showing an area. Here's a scale bar, 100 kilometers. This feature is mostly black, although there are some areas that are not quite so black in the radar data. The radar system has 5 transmitters, 5 different bands that operate at the same frequency but have slightly different sensitivities. So when these are put together, you don't quite get a uniform image. But this is a seam, this is not a highway. This is a seam in the radar beams, and so is this. But you know, clearly this looks like a feature that is a basin of liquid that is also flowing over into areas that are feeding it here, tributaries, rivers, whatever. No one has dipped their toes in this, so we can't know for sure if it's liquid, but almost everything about this suggests that it is. In the southern hemisphere, and now more recently in the northern hemisphere, 2 of these features have been spectroscopically analyzed, and ethane has been found. Methane is very difficult to see on the surface because there's so much methane in the atmosphere. So we couldn't see methane in the lakes even if it were there, and one suspects that it's there. They have at 2 centimeters wavelength when the radar is used as a passive radiometer. These have the right brightness, temperature, contrast relative to the adjoining surface to be hydrocarbons, and they are very, very smooth because they produce sea glints. So this is one of these features. This is Kraken Mari. The other one was Ligeia Mari. This is even larger, about 1,000 kilometers in extent. Here it is at one angle with a low phase angle, and here it is at a slightly different phase angle near zero, where you get a sea glint, a reflection off of a very smooth surface. Now it could be a glassy surface, but it's very hard to think of anything, natural materials, over this extent that would actually be glassy and solid. Plausibly, these are liquids. It'd be nice to go actually land in them someday to find out for sure, and I'll talk about that. Okay, here's a southern hemisphere lake, Ontario Lacus. This is a little bit smaller. It's about 270 kilometers from top to bottom. And this is an image taken with the imaging science system, the camera on Cassini, affected by the haze in the atmosphere, so the resolution's not so good. This was taken in 2005. Now, watch this very carefully. This is going to be a radar image from 2009. Okay, so 2 things. One is this is a lot clearer, but the other is you can see that it's actually shrunk. And while radar penetrates more deeply than imaging does, there's actually some altimetry and topography available. And Alex Hayes and colleagues showed convincingly that this is a real shrinkage of the lake over that 4-year period. This is Marina del Rey, and there are quite a few expensive yachts there. Either that or that's a bunny rabbit. But anyway, so these are not clouds. This is rough terrain. These are mountains at the end. And this would be very familiar to anyone who's seen desert playas, for example, a racetrack playa, where one end is bounded by very rough terrain and the other end by smooth terrain. A lot of geological analysis has been done here. There are beaches. There are a number of features that would be familiar to geologists studying lacustrine geology on the Earth. The shrinkage in the lake size over that 4-year period can be explained by recalling that Titan has seasons like the Earth. The axis of Saturn and Titan, both the rotation axes are tilted by the same amount, 27 degrees, a little bit more than the tilt of our own axis. The seasons are long because Saturn and Titan take 29 years to go around the Sun, so each season is about 7 years long. Cassini arrived in late southern summer, and between 2005 and 2009, summer progressed almost to the end, almost to equinox. So in the south, sunlight was focused on the southern hemisphere, and it would be natural to expect evaporation. This amount of evaporation, based on the loss here and on the topography, the slope that was obtained on the edges of the lake when the radar was used as an altimeter, leads to a calculation of a loss of about 100 cubic kilometers of methane liquid, if it's methane, over that period of time. And that's just about what you would expect for the evaporation of methane. Now, methane is very volatile. This is a plot of its vapor pressure versus temperature, along with other possible constituents. Much more volatile than ethane. Here's the temperature range for the lakes. So methane would actually evaporate in an energy-limited way. That is, the lake would actually begin to cool as the methane evaporates. And so the rate of evaporation is determined by the amount of sunlight available, not directly by the vapor pressure. That, by the way, would limit then the evaporation of any ethane in the lake, and ethane's been seen spectroscopically. And it's about the right amount for 5 years. The shrinkage is just about right. So evidently methane has been evaporating over that period of time. Now on the edges of the lake, some spectroscopy done with the Cassini near-infrared mapping spectrometer by Marissa Morricone and colleagues at IFSI in Rome have identified a number of constituents, propane, acetylene, even methane, and ethane showing up on the edges. If the lake is predominantly methane, it's actually hard to see because there's so much methane in the lake, but it's possible to pull some of that out from the edges if the soil is wet. And then some HCN and other compounds too. So these lakes retreat and expand seasonally. They hydrate and dehydrate, if you will, which makes this chemically potentially interesting. But there's another cycle other than the seasonal cycle of 30 years on Titan. Saturn's orbit around the Sun is eccentric. And that eccentricity leads to a variation of about 7% between the amount of insolation, the solar power received at present during the first day of summer in the south versus the first day of summer in the north. But that eccentric orbit of Saturn around the Sun actually precesses because of the effect of the other planets. And it precesses on a time scale of 50,000 years. And then there are other effects associated with the eccentricity of the orbit that vary on longer time scales. And this sounds somewhat like the Milankovitch cycles on the Earth. So this is work by Odette Aronson and colleagues showing the difference in the peak insolation north to south over time. This is over the last 1,000 years. But there are also 50,000 year and 100,000 year cycles. And currently the southern hemisphere is receiving the maximum insolation. The other interesting effect is that methane is less viscous than water by a factor of a few, whereas ethane is more viscous than water by a factor of a few, and propane even more so. So there are some very interesting cycles that should be going on in these lakes and seas. The seasonal cycle is that methane is being moved from one hemisphere to the other. The lakes are going from being methane rich in the winter to ethane-rich in the summer, and that implies higher viscosity for the lakes in the summer and lower viscosity in the winter. And then on these much longer time scales, 50,000-year time scales, you can easily evaporate all of the ethane and the propane, and so you may completely dry these lakes out and leave precipitates. And indeed, at the moment, the southern hemisphere has far fewer lakes than the northern hemisphere does. So a lot of this has to be worked out in more detail, but this is clearly something that is more complex and has no direct analogy with the way the Earth's hydrologic cycle works. But certainly in terms of the methane equivalent of hydration and dehydration, that is very much present. There are some mysteries. The hydrogen abundance in Titan's atmosphere should be a constant until you get close to the top where hydrogen's escaping. But one very careful analysis by Darrell Strobel of several different types of Cassini data suggests that there's also a sink of hydrogen at Titan's surface, which was not predicted and is unexpected. There's still some debate about the validity of the interpretation, but if it's true, it's quite interesting. And acetylene is actually underabundant in surface deposits. We see it in the atmosphere, but it doesn't show up very well in the near-infrared data. Instead, benzene, C6H6, shows up to a much larger extent. And so evidently the acetylene is being converted to benzene, so there is surface chemistry going on. And finally, the big mystery is if methane has been supplied from the deep interior over time, which certainly the amount of dune material, these vast dune fields of organics, suggests that it has. Why don't we see a lot of ethane on the surface? It's confined to the lakes. Where has the ethane gone? Has it been soaked down into the crust? Is it being consumed by something? This now is really a significant question. So all these mysteries lead to lots of interesting speculations. Is there a kind of methanogenic chemistry where hydrogen is being used up along with acetylene to regenerate small amounts of methane, allowing for the generation of energy by some abiotic or protobiotic system? There's very simple chemistry going on where acetylene gets converted to benzene. Benzene can actually adsorb hydrogen, and so it may be that some of the hydrogen loss, if there's enough benzene around, is due to that adsorption. This is an entirely, yet another lecture that would take an hour to go through. And Titan continues to surprise us. It is now April on Titan. This is the way Titan has looked through the northern winter and on to the first approach of equinox. And this is the way Titan looked late last year at equinox. So these are not merely little wispy clouds, these are storm clouds. Imaging of Titan's surface over this period as Titan passed through equinox, northern spring, southern fall, showed areas on Titan's surface where these clouds passed through as having very dramatic changes. So this area, you see this little feature is a sort of a fiducial point. See what's happened to the area below it there, and then it's gone back to being bright again. The amount of darkening that occurred under these storm systems covered about 500,000 square kilometers. And so the interpretation is that there was precipitation of methane. The soil was at least made damp. Damp soil appears much darker at optical wavelengths than dry sand, whether it's ice sand or silica sand. And so we may in fact be seeing widespread methane rainstorm events. Now as Titan passes through equinox, the change in the circulation would in fact lead to instability in the equator as something called the intertropical convergence zone moves from the south to the north. So this is understandable, and it may explain features that Huygens saw during its descent in the equatorial region, these beautiful dendritic features with channels that are about 10 or 20 meters across. There were stereo images here, and this is a hill that's 500 meters high roughly. These dendritic features follow the topography of the hill beautifully. So there is precipitation on Titan, storms, winds which move the dunes, hydration and dehydration in the hydrocarbon sense of the lakes and seas, Everything you want to think of in a hydrologic cycle is there on Titan. And so we have to ask the question, is the one thing that is missing from that hydrologic cycle, in fact, not missing on Titan? Could we possibly imagine that Titan could host life on its surface? Now, there is pretty good evidence that Titan has a liquid water ocean under its ice crust, but I'm not going to be talking about that. The base of that ocean would have to have not rock, but high-pressure ice, and that may be less interesting from the life point of view. But at the surface, there are liquids, admittedly not aqueous liquids, hydrocarbon liquids. So you can be a water, how shall I put it? You can be, lost the word now, even in English. You can be prejudiced and say that water only is the only solvent available for life, or you can ask the question, could liquid hydrocarbons be a medium that could support either life or a kind of chemistry that could show you how completely abiotic chemistry evolves toward prebiotic and transitional protobiotic chemistry. Water has a lot of admitted advantages. It's an excellent solvent for salts. It's polar. It provides an inside and an outside for biopolymers because these properties allow polymers to be hydrophilic and hydrophobic, and therefore to twist, to make structures like in DNA, to form vesicles, to create enclosures, all sorts of things that from the point of view of prebiotic chemistry seem to be important, and the behavior of the basic biomolecules would seem to depend on water as well. However, Steve Benner and colleagues have pointed out that there are some things about water that are rather troubling for biology, and that biology has gotten around. I'll mention one. There's a whole, or two actually, there's a whole class of potential types of bonding among organic molecules that involve hydrogen bonding. Those are completely blocked in water because water is a very strongly hydrogen bonding liquid itself, and so all the hydrogen bonding occurs between the water molecules, not the organic molecules. CN bonds are pretty much ruled out in liquid water, and so life depends on carbon-oxygen bonds, whereas there's a whole class of carbon-nitrogen bonds that could do some interesting organic chemistry as well that can't be done in water. This has been, again, these are some of the ideas of Benner and colleagues. So, obviously methane and ethane have serious disadvantages having to do with their lack of polarity, but you might be able to salt these lakes with small amounts of polar hydrocarbons. There are non-zero solubilities here that might provide you with a little bit of polarity to imitate what happens in polar water. But in ethane and methane, organic molecules can hydrogen bond, which is not possible in water. There are CN bonds that are available that are not available in water. And if you like, there are some carbon-oxygen compounds that can be made resulting from interaction between the ice at the bottom of the lake and the lake itself. So Benner's point is that one should not rule out ethane and methane as a possible host for life, but it would be a very exotic kind of life that would have essentially no biochemical relationship with the life as we know it on the Earth. And this actually is a big advantage that Titan has over other astrobiological targets for several reasons. The first is that if one were to go to Titan and be able to do analyses that showed that the chemistry that was going on was self-organizing, involved catalysts that were regenerated in the reactions, possibly including molecules that actually carried the information needed to rebuild these catalysts and build the structures within which the chemistry was done, you would probably call this a very primitive form of life, or even, let's say, proto-life. Something that cannot be done in the laboratory on the Earth, and something that we do not see in the natural environments of the Earth because life has co-opted essentially all of the organic chemistry that we see. So life in an ethane-methane sea would be so different from life on the Earth because of the ethane-methane versus water that you would immediately conclude that it involved a second separate origin of life, that it was not life that was transported from the Earth or from Mars or from anywhere else and contaminated Titan. It was a homegrown, unique, original kind of life that was designed or evolved around ethane and methane. And so life in ethane methane seas on Titan is a far more stringent test of a separate second origin of life than what one might find on Mars, Europa, or Enceladus, unless you could study these enough to be able to conclude that they really had a separate origin. And that would be difficult to do because the rooting of those could be very deep in the tree of life. They could have been transported early in the Earth's history. But again, life in a hydrocarbon sea is so fundamentally different that it had a second separate origin. And again, this whole argument hinges on the idea that within our own solar system, the impact exchange of material between bodies, panspermia, is in fact something that really happens and could in fact have distributed liquid water-based life throughout the solar system into other environments where liquid water exists. So instead of this, the relationship between life on the Earth and life on Titan is rooted not at the polymer level or even the monomer level, but only at the element level. That's where the rooting is. And so it had a separate origin. There are two other advantages to looking for life on Titan. Someone asked about planetary protection issues. No planetary protection issues here. Any bacteria that happened to have hitched a ride on a probe would be immediately sterilized in this environment. It could not survive in a liquid methane-ethane lake. There are some places you don't want to land on Titan where something might get into vents that could lead to the liquid water ocean, but the lakes themselves are perfectly safe. Finally, easy access to the lakes. No radiation, no drilling. You just do what the European Space Agency did in 2005. Okay, land a probe on Titan. The only problem with the Huygens mission is that we landed at the equator instead of at the poles. But no one knew that there were liquid seas and lakes at the poles and not at the equator. The equator was the easier target. So, I would point out that a National Academy of Science committee that was chaired by my colleague John Barros said in 2007, if life is an intrinsic property of chemical reactivity, life should exist on Titan. If life does not exist on Titan, we would have to argue that life is not an intrinsic property of the reactivity of carbon-containing molecules, but something that depends in a special way on the properties of liquid water, and we would immediately eliminate a vast number of other possibilities that could occur throughout the cosmos, which I'll talk about tomorrow. That's an important statement, and in order to address this statement, we have to go to Titan and sample the liquid hydrocarbon seas. So how do we do that? We do that very easily. Okay? You do it for the cost of a discovery mission. So because this is actually a proposed discovery mission and is still being evaluated, this is not actually a picture of the probe as we proposed it. But there is a proposal in called the Kraken Mari Explorer at the level of a discovery mission, which would land just the way Huygens landed at the equator in one of the large seas of Titan. It would sample those seas chemically, make other kinds of measurements, and basically float on those seas for about 6 Titan days, which would be about 90 Earth days, with a good chance actually of making it to one of the shores based on the wind patterns. So it would carry a camera as well. There would be no orbiter. It would be direct to Earth transmission. That limits the data rate, but it greatly reduces the cost of this mission. And so this is not a $4 billion mission. This is a $500 million mission, $500 million. And this is not a difficult technological feat. This was done in 2005 at the equator of Titan, and landing in liquid is something that we all, I think, know how to do. We've done it ourselves in swimming pools, and we've all played around with boats and so on. You can't imagine the number of engineers who've said, oh, landing on liquid, how do you do that? Well, hold on, let me grab you and throw you into this swimming pool here and I'll show you. This is not difficult to do. So this last slide is a little hard to see the bottom, but this is a single image. This is the silhouette of Enceladus, but a part that doesn't include the plumes. Here are the rings of Saturn, and here's Titan behind it, all in one image from Cassini. If we are really serious about testing the question of whether life can occur in any chemical environment where there are organic molecules, liquids, hydration, dehydration cycles, outgassing and geologic activity, which evidently Titan has had, and sources of free energy, even if they're not the kinds that we have on the Earth. If we're serious about testing whether life is a common cosmic phenomenon, we have to go back to the Saturn system. Thank you. So I'll put the collection plate in the back here, because I'm not sure that NASA's going to go for this mission. Yes?
What's the power generation system of the probe?
It's RTGs. Now, the interesting thing about this particular discovery opportunity, and only this one, is that, oh dear, is that NASA, that came off, I knew that would happen. NASA wants to test this new generation Stirling engine RTG, and in the AO said that they would supply it at essentially no cost as government furnished equipment. So whereas previous discovery opportunities were all solar powered, this one we can use radioactive power. Jim.
Yeah, I have a biology question. I think this is a great mission, so I hope it gets selected. But is there, I mean, it's very cold on Titan.
Yes,
so
it is.
The question, maybe this is more for John, but is there something about chemical reactions go very slowly at cold temperatures, and so is there anything about rates of reactions that might be important for having life?
Well, I'll take a crack at this and then give it to John. We have a colleague named Mark Smith who's actually now at the University of Houston. He was at the University of Arizona. And he's studied reactions at low temperatures, initially with interstellar molecules and then for Titan. If you look at reaction rates that are extrapolated from high temperatures, the answer is, yeah, these go really, really slowly. The problem, of course, is that the rate mechanisms that you have at high temperature are so fast that they disguise other mechanisms that may become important at very low temperatures, so that if you extrapolate along an Arrhenius relationship and you don't know that there's another reaction mechanism that is slow, but not as slow as what you would get for your extrapolation, you will underestimate the reaction rates at 94 Kelvin. So he has argued that some of the, or many of the organic reactions may actually go faster than one expects at 94 Kelvin if your expectation is based on a simple extrapolation along an inverse exponential e to the minus a over t. The problem is you've got to measure those rates at 94 Kelvin, and that's really difficult to do. But yes, it's slower, but it may not be as slow as we would fear based on a simple extrapolation. You want to take a crack at this?
Yeah, so the only thing I would say, and of course if I were to choose one big mission to go to, it would be to Titan for a lot of the reasons that Jonathan mentioned. Things go slower in water as you decrease the temperature because water becomes either viscous or to maintain its liquid, you're adding something to make it even go slower, like more salts. So if I take an enzyme, for example, that cannot work in water at 10 degrees Celsius, for example, and I place it in 50% solvent and 50% water, it is active at a relatively good rate at minus 100 degrees Celsius. So I'm not, the temperature is, for me, is not the issue in this. I am interested, for example, in getting to know more about the chemistry besides the very reduced carbon. I'd like to know the oxidation reduction potential of inorganic elements, etc., in these systems. Because I don't care what kind of life you have, it can be a completely different from Earth life, but you still need oxidation-reduction reactions to go on. And you're going to need more oxidative states in that carbon. Something's going to have to take that carbon to an oxidative state.
Yeah.
The nitrogen won't do it unless nitrogen is coupled with oxygen.
Yeah. Matt Pasek, who was a NASA astrobiology postdoctoral fellow and had gotten his PhD at Arizona, worked with several of us and just finished, well, just had a paper published in which we calculated how much and what kinds of phosphorus compounds we would expect on the surface. You don't just have to get them out of the interior, you also get them from meteorites that are falling down over the history of the solar system. So these are important issues, and we've tried to take a crack at this for at least one of those elements. So I'd be happy to send you a copy of this.
Yeah, no, as I said, and landing there and landing on some decent places, you would get a complete panoply of chemistry pretty rapidly. Mm-hmm. And that would be, I mean, if I had all the ingredients in front of me, like I do when I want to cook, and if I had all those ingredients, I could probably tell you what would be an energetic set of reactions. But I don't have all those ingredients from what you told me. Enceladus, however, boy, I can just go away and have fun playing with that one.
I'm not sure if you mentioned that, but is there evidence for lightning or impacts?
There's plenty of evidence for impacts. There are over 70 identified impact craters. The smaller impactors get shielded out by the atmosphere. And evidently the surface has been resurfaced on Titan. We're talking about Titan now. Has been resurfaced within the last 500 million years. That's based on the crater count. So impacts have melted the crust and provided periods in which liquid water has existed for some period of time. No lightning has been detected. There are evidently methane storms, not just at the equator, but there was another episode near the South Pole just as Cassini was arriving, which you expect because that was southern summer. And those really looked like convective cells. They had the right appearance from above. But the methane's nonpolar, so when you generate the raindrops, even though there is a background electric field that Huygens did measure on Titan, there's no way through droplet fragmentation to increase the potential and create a breakdown potential. So these are probably not thunderstorms. These are just plain old rainstorms. But I will say one thing. If you're standing under one of these with the typical wind speeds and the fall speeds of the droplets, the rainstorm would hit you on the ground after the cloud passed over you because the gravity is low, and so the raindrop sedimentation rate is much lower than on Earth. So there are always sun showers. Yes, one other question. Yes?
Yeah, maybe I missed what I was dreaming of staying on Titan, but what exactly detection would say you I'm 100% sure it's life on Titan, and which kind of data would you send back to Earth saying, okay, 100% this is life, or we are completely...
Well, that's a great dinner conversation because, I mean, obviously if you brought the world's most elaborate lab and you were able to collect things and actually see whether there were genetic mechanisms and that sort of thing, you could do something. With the instrumentation that we have, the best that you can do is look to see if the chemistry in the lakes is distinctly different from that in the atmosphere, and in particular, whether there were particular species that seemed to be preferred, that didn't follow a simple pattern of a decline in abundance versus molecular weight, for example. If people have looked at this question over the years as to what would be a simple single chemical test, and obviously there is none, but a pattern in the abundance of the organic molecules, a preference for even versus odd number carbon, for particular molecular weights, that kind of thing, could indicate that there was a set of catalytic cycles going on in these lakes that, if not life, would be an interesting precursor to life, something you don't have in very simple, dumb, abiotic organic chemistry, but is something on the way to life. Okay, so